All right. So chapter 14 is all about rational functions. Rational functions are something that can be written in the form of p of x over q of x, where p and q are polynomials. And obviously q of x is not the zero polynomial. Why can't q of x be zero polynomial? Can't but divide by 0. Yeah. Okay. So first thing we'll talk about is calculating domains. So let's just say that we have this rational function here, x plus 4 over 2x minus 1. When we have a fraction or a division problem like this, where can we get in trouble? Dividing by 0. So the domain will just be everything except where the denominator is 0. So how do I write that using proper interval notation? I do negative infinity up to a half, and then a half to positive infinity. Note that I'm using the parentheses there to indicate that the 1/2 is not included. Any questions so far? Okay. Next example, I should probably say, has to be a function to have a domain, right? That was almost real silly, Mr. Hulick. Same idea though, right? We're just gonna set the denominator not equal to 0. How am I going to solve something like x cubed minus 4x not equal to 0? What do I want to do first to solve that anyways? It's pretty algebra 2, algebra 1-y kind of question. Should be pretty capable of answering that. What do I want to do first? Do you notice anything in common? Yeah, factor an x out. Good gravy, guys. Let's chalk that up to being 9:25 on a Monday. Okay, then what do you see? Difference of 2 squares, so we can factor some more. And then you can zero product property. And we get 3 solutions, right? Everybody's cool with that? So write this in proper interval notation. I'll do negative infinity to the smallest, union the smallest to the middle, union middle to the biggest, union biggest to positive infinity. Does that feel okay with you guys? The big thing there when you're writing your intervals is make sure you're writing things in the right order, right? You go small to big all the way through. Everything is covered except for those 3 values in which you know that you get a 0 denominator. All right, we're going to talk now about sketching a graph for one of these rational functions. For that, we need to worry about certain key features. First is the vertical asymptote. How do I find that? It's the reduced denominator set equal to 0 and solved. Next thing we need are the end behaviors. There's actually 3 cases here. And I'm going to just say that we have some, let's do this. So let's say we're sketching the graph for this. There, we'll take that. All right, end behaviors. So case 1, degree of p of x is less than the degree for q of x. So either you have a horizontal asymptote or end behavior at y equals 0. Case 2, where the degrees are equal. So if the degrees are equal, you're going to take the leading coefficient of p of x divided by the leading coefficient of q of x. So I'm just abbreviating leading coefficient as LC. And then the last case is where the degree of the numerator is bigger than the degree of the denominator. This means you're going to have a slant or oblique asymptote. Those two terms get used interchangeably. And we're going to find that using polynomial division. We'll do an example where we actually show you how, again, remind you how to find that. So, next thing we're going to be looking for the zeros. To find those, we're just going to take the numerator, set it equal to 0, and solve. The y-intercepts, we're just going to plug 0 in for x. And then the last thing we might have to worry about, it's rare, but it can happen, is removable discontinuity. Discontinuity. And this can only occur if you have to do some reducing. Doesn't guarantee that you're going to get a removable discontinuity if you have to reduce, but that's the only time it can occur, is if you have to do any reducing in your fraction. All right. We're going to do 3 examples of this. And we'll move on to the next stuffs. Cool? Why 3 examples, do you suppose? Yeah, we'll get an example for each of the 3 cases. Yeah, somebody was using their noodle there. That's slang for your brain. I don't know, man. Your arm? Yeah. People say noodle arm, right? You can't really throw a baseball or something. Yeah. So there. All right. So our first example is x minus 1 over x minus 2. Vertical asymptotes. To find those I meant this should supposed to be 4. I'm sorry. Take the denominator, set it equal to 0, and solve. Hopefully you recognize that that's also a difference of 2 squares. It's the same difference of 2 squares that we noticed in the earlier example. There's my 2 vertical asymptotes. All right. What did we forget to do, though, before we found this vertical asymptote? We should check to see if this is reduced. Can this fraction reduce? No. Because the factors on top are just x minus 1. The factors on the bottom are x minus 2, x plus 2. None of them are identical. There's no reducing to do. Should always make a check quickly in the beginning to make sure on that. This one, it was obvious, I think, upon looking at it, that it wasn't going to reduce, but I should make mention that we should be checking that first. Okay. End behaviors, we have to compare to the degrees. What's the degree for the numerator? 1. The biggest exponent on the variable. What's the degree on the denominator? Okay, so which case are we in? Case 1. So just y equals 0. That's really nice. Next thing up are the zeros. How do we find the zeros? Numerator set equal to 0. That was easy. Next up is y-intercept. So just get 1/4 from that. When I plug 0 in for x, everybody's cool with that? And then, since there's no reducing, we can't have any removable discontinuity. So far, so good? If I'm going too fast or you're confused by anything, please speak up. Oh boy. That's not what I wanted that to look like at all. All right. So I'm going to start by putting in my asymptotes and end behaviors. Let's see. 1, 2, 1, 2, buckle my shoe. Okay, and then we have that. So far, so good. All right, I have a 0 there at 1, and I have a y-intercept at 1/4. I've drawn in all my key features now that I have, right? Everybody agree? So what I need to do now is figure out what's happening at these asymptotes. For example, is on the left-hand side of this vertical asymptote, should my graph be going up or down? Everybody's cool with that? To do that, we're going to just plug in some values into our function and see whether things are getting bigger or smaller as we get closer to that asymptote. Grace? Sure. So I'm going to use my calculator to do that, plugging in. because, well, it's kind of a hassle. The easiest way, in my opinion, to do this is I'm going to enter my equation into the y equals menu, and then I'm going to use the vars, y vars function y1. So I'm going to pick some values that are close to the left-hand side of this asymptote, so maybe negative 2.1. And then if I get a little bit closer, like maybe negative 2.01, I notice that I'm getting smaller the closer I'm getting to that asymptote, which would tell me that my arrow should be pointing down on my graph. So if I'm staying between my end behavior and my asymptote, it means that my graph should look like that over there. Now I need to check the same thing on the right side of that asymptote. So I'm going to pick two values that are just a little bit bigger than negative 2. So negative 1.9 and then negative 1.99. I notice there as I'm getting closer, we're getting bigger. So I know that my graph is going to go and do this, at least until I get to that 0. But again, I don't know whether the graph should be going up or down at that 0. So I'm going to check what's happening at the left-hand side of this asymptote. So that would be positive 1.9. And then positive 1.99. So there we're getting smaller, so I know we should be going down. And then the last check is to see what's happening over here. So look at the other side. We'll do positive 2.1 and then positive 2.01. Again, I got bigger there, so I know that I am up in this section there. Now, notice I did use my calculator to do this, but only just to make the arithmetic easier. I could have done the same thing, plugging those values in for x and evaluating with like a 4-function calculator back when Mr. Kulik had to do this, when that's what we had to use. I understand that if you're going to type it into the y equals menu, why can't I just press graph and look at the picture and copy it down? That's not the point. The point is showing you that you could do this without the graphing function, that it's purely like a, like a 4-function calculator is sufficient to do something like this, to sketch the graph. Okay? And I'm just using that option on my graphing calculator just to make my life a little bit more, like I have to press less buttons, you know what I mean? It's just a pain in the tuchus, you know? I'm gonna take it easy on my poor tuchus. All right. All right, next example. Vertical asymptote. Boy, that was a weird way of pronouncing that. What do I do? Yeah, denominator equal to 0. What should I have done first? Check to see if it could reduce. Now, clearly, since both terms are degree 1 with leading coefficient 1, there's no reducing to do here, like very obvious. So, like, there's not much checking to check, but should think about that. Okay, end behaviors. So this is degree 1, and this is degree 1. So this is case 2. So I'm going to take the leading coefficient of the numerator, that's negative 1, over the leading coefficient of the denominator, that's 1. So my asymptote or end behavior is at negative 1. Questions so far? Okay. Zeros, what do I do? Numerator equal to 0, get 2. Y-intercept, what do I do? Plug in 0, that gives me 2/3. And since there's no reducing, I can't have any removal discontinuity. So that feels pretty good there, right? Yuck. Hey. Oh, OneNote. You are being so special today. Okay. Well, you're responding. Why can't we do anything? I don't know. I don't know, guys. And then why is it giving me the dumbest looking graph ever? I don't know. I think basically it just wants to fight. Bring it on, OneNote. I'll take you. All right. All right, so I got my vertical asymptote at -3. I got my horizontal end behavior there at -1. Got my x-intercept at 2 and my y-intercept at 2/3. And that's pretty nice because I can already tell what has to be happening on the right-hand side of that graph, right? The only way that I can go through those 2 points and still follow the asymptotes is if it's doing that. Everybody agree? So I don't even have to check the left-hand side of that vertical asymptote. I just have to see what's or the right-hand side. I just have to see what's happening on the left. Well, alrighty then. That's not so bad. So I'll go and type in my new equation. And then we'll just do -3.1 and -3.01. And it looks like we're going down. And that'll do. You guys happy with that? Yeah. Okay. All right. Vertical asymptote. Probably here it's worth factoring that numerator and double checking just to make sure if there's any reducing. There's not, but that's, have to be careful there, right? Any questions on how I factored that? You guys remember how to factor stuff like that? So we are in case 3. So for case 3, we need to do a polynomial division. I know, I'm excited too. In general, I always just set up long division for these. Now, I admit in this particular case, we could do the synthetic division version, but That is often not the case. Remember, synthetic division you can only do when your divisor is degree 1 with leading coefficient 1. Now, if it's degree 1 and its leading coefficient isn't 1, you can make some kind of major modifications and still kind of get it to work. But in general, just do the long division, you're usually better off. All right, so what we're going to do is we're going to ask ourselves, what times x gives us x squared? X. So I write the x up top. I multiply it to both parts of my divisor and then subtract down. X squared minus x squared is 0. Negative 4x minus 2x is negative 6x. That is the place where most students make their mistake, is forgetting that this is a subtraction problem and making sure that they're subtracting. Okay. We then ask ourselves, okay, what times x gives me negative 6x? That would be negative 6. Distribute that over there. 2. Subtract down. Negative 6x minus a negative 6x is 0. Positive 5 minus a negative 12 is 17. So what does this tell me? It tells me that my function f of x is equal to x minus 6 plus 17 over x plus 2. But the part that I care about is only the quotient. That's the piece that I need for my end behavior, is just the quotient part. The remainder does not matter to me right now. Well, no, in this context. I mean, if it was a different problem, yes, the remainder could matter, but like with what we're doing with it, no, the remainder, we don't care. So far, so good? Everybody kind of remember that? Zeros. That's nice because remember to check to see if this could reduce. I already factored the numerator. So I have that information already. The y-intercept, easy, just plugging 0 in. And we weren't able to do any reducing, so there's no discontinuity there. Everybody's cool? Ah, shoot. Okay. We're also going to need a set of points to graph the line y equals negative 6. Okay. that. Shrink that down a little bit for us. Oh my gosh. Oh my gosh. Hey guys. That was supposed to be a -5. Because I factored it right up there. Goodness gracious. So that should be -5/2. I know. I'm really sad too. It's not a big deal. Look, it's going to just be a couple of things. So, admittedly, that value should be -5, but all it's going to do is change the remainder. So this remainder should be 7 instead of 17, but like who gives a hoot? Didn't matter to us. So that's it. Basically, the only thing that really changed for us was this, because thankfully Mr. Kulik factored the thing the way it was supposed to look rather than what he wrote down, which saves us a little bit of hassle. I'm sorry! All right, so one thing I can do right away, oops, use the blue, is I can tell how to draw that piece based on those 3 points in the asymptotes. Everybody cool there? That should be pretty obvious. The question becomes, do I draw my other thing in there, right? To check that, we'll do the same check that we did before. So I have -78, which already I have a pretty good idea of which is going to be going on. And then 0,1, we'll get a little bit closer. Really negative, so should be pointing down. So I am down in here. Feel okay? You guys remember this from last year? We did this last year, right? Some of us do, maybe more than others. That's okay. All right. Next up, we're going to be talking about solving rational equations. There's no theoretical piece to this section. It's just going to be talking about solving techniques. So we'll talk about a couple different approaches that we could use. They're all kind of doing the same thing, so just kind of whichever seems the easiest or most convenient or obvious to you is fine. So if I have something like this, what's your first instinct? Okay, second, if you're going to solve this algebraically, what's your first instinct? Ask a non-specific question. Who knows what you're going to get for an answer? That's my own fault. I'd probably get rid of the fraction, right? How do you get rid of the fraction? Multiply both sides by x, right? I call this technique clearing fractions, is how I refer to this. Everybody's cool? What I have is a quadratic equation. To solve a quadratic equation, I get everything onto one side. And then I try to either typically factor, use the quadratic formula. Here I know its leading coefficient is 1, so if it's factorable, it should be quite easy. Two things that multiply give me positive 3 and add to give me negative 4 are negative 3 and negative 1. So my solutions are 1 and 3. Am I done? No, what do I still have to do? Check. What am I checking for? Okay, what would indicate an extraneous solution? If you get a zero denominator, exactly right. So if I plug in 3, that's fine. Plug in 1, that's fine. Neither one of those give me a zero denominator. I am done. Okay, what else could have you done here? Well, I could subtract x from both sides to set up a ratio of two fractions. When I have one fraction equal to another fraction, I can then cross multiply. And now I'm basically at the same spot I was before, right? That's a reasonable thing to do. What else could you do? You could make a common denominator to both sides. So that common denominator would be x. Once you've done that, once both sides have the same denominator, you can just set the numerators equal to each other. Right? Everybody's okay with that? And then the other thing you could do is if you move everything onto one side and make a common denominator, so that it's equal to 0, again, you can just take the numerators and set them equal to each other, and you're done. Any of these approaches are fine. They're really all doing the same thing. So it's just a matter of like which one seems algebraically the easiest to get to, or the one that you're most comfortable with. But they're all really doing the same thing. Okay? In general, Mr. Kulik's preference is he does clearing fractions unless there's something else that's like considerably simpler to do. In general, he does that because he's found in his experience that clearing fractions is almost always going to be at least the easiest and often, and then rarely ever the hardest way of doing something. So seems like it's usually the best option the majority of the time in his experience, so he likes to do that. Plus, it gets rid of the fractions the soonest, which is usually better for everybody, right? All right, let's take a look at this one. What do you want to do first? Okay, what are we going to do to clear fractions? Multiply both sides by x plus 1. Notice here that this quadratic that we've gotten is once again factorable. So that makes life pretty easy in terms of the solving. Do both of those answers work? Yes. Again, all you're doing is checking to see when you plug it in for x, do you get a zero denominator? There's only one denominator to check, and obviously it doesn't. So far, so good. Usually most of us feel pretty good about these kind of solving problems. This is just like straight up Algebra 1 stuff, or I'm sorry, Algebra 2 stuff. You probably didn't do this in your Algebra 1 class. All right, what do you want to do here? You could try doing common denominator. Before I do anything, though, I would factor the quadratic in my denominator so I can see if this is actually really a pain in the butt problem or not so bad. Which now, this is not so bad, right? Notice that both factors in my denominators are the factors in that quadratic. So I would still clear fractions here. What would I use to clear fractions with? X minus 3 times x minus 1. Yeah. Everybody's cool how I did that? Okay, distribute things through. Combine like terms and move everything onto the same side. That looks a lot like a 6. To solve this quadratic, again, either factor, or we can use the quadratic formula. Notice the leading coefficient here is not 1. So if you were to try to factor this, this is the one that kind of takes the long factoring method where you have to do the factor by grouping. Alternatively, you can just use the quadratic formula. I would probably use the quadratic formula in this case. Now, this one certainly does factor and it works and it's not that hard to get to. But the quadratic formula also is pretty easy, so if I'm ever in doubt as to whether something is that factorable or not, I just quadratic formula it because I know. So 25 minus a negative 24 is 49. Square root of 49 is 7. 12 or 5 plus 7 is 12 divided by 2 is 6. And then 5 minus 7 is negative 2 divided by... Oh, shoot. That's a 2 times 2. That's a 4 down there. Good gravy, Mr. Kulik. I know, guys. I know. Okay. All right. Are we done? No. What do we still have to do? Check. Do they both work? No. No! Which one doesn't? The 3. Everybody's cool with why the 3 is a problem? Yes, of course. And again, as a reminder, it only needs to be a problem once, right? Any fraction where you get that 0 denominator is no bueno. All right, one more example, and we're going to move on. All right, put on your imagination caps. Pretend you're a farmer. And you're going to make a rectangular fence around your field. You're going to fence in a field that has to have an area of 500 square feet. And you want to minimize the amount of fencing that you need to use to fence in that area. What you going to do? So when we talk about the fencing, what's the fencing equivalent to? The perimeter. So let's give this side lengths a name. The perimeter would be, in this case, 2L plus 2W. And the area in this case would be L times W. What I'm going to do is I'm going to create a system of 2 equations now using area and perimeter. So I know the area is 500. So I'm going to solve that equation for either L or W. It doesn't really matter. And then I'm going to substitute it back in to my perimeter equation. So this is a function of perimeter in terms of W, right? Everybody's cool with that? To find where that is minimum, I'm going to graph this function and look for its minimum. What do I have to be careful about when doing this, though? What do I have to be careful about if I'm just going to graph this and find the minimum? Are all values of x valid to check? No, right? X needs to be positive for sure, right? Okay. So let's start setting a window. So I'm going to set my x minimum at 0. I'll set my x max. I don't know. I figure a 500 by 1 is not going to be the cheapest fencing. Everybody agree with that? But it's plausible. So maybe I'll go 0 to 500. And then the perimeter for a 500 foot on one side, it means the other side is length 1. So it'd be like 1,002 for the perimeter. So I'll make the y max just 1,000, since I know that that's a garbage answer anyways. And then let's just hit graph and take a look at what we get here. So it looks like my minimum is happening somewhere over here. Everybody agree with that? So second trace, minimum command. I'm going to scroll over till I see that I'm left of that. So I'm just kind of watching the y values for when they start getting bigger again. And there, well, that's perfect. I'm on the asymptote anyway, so let's just do there. And then I'll scroll right. And that's probably good enough because they've just been getting bigger now for a while. So I'll press enter again. Guess doesn't matter. So 22.36 for W and about 89.44 for the perimeter. Note now that we found W, we could find L. How do I do that? Just using that, right? Just for grins, so we can tell Farmer Fran here exactly the dimensions here. What do you notice? Yeah, what shape are we actually making here? A square. This is not a coincidence in general. Like if you're looking for the type of shape that minimizes the perimeter for a fixed area, it's always going to be the regular figure unless you have some like, oh, I can use the side of a wall as a fence, so like I get one side for free, or you know, something like that. But if it's just like, yeah, the fencing is the entire perimeter, to minimize the perimeter, use a regular figure. All right, last section in 14 is about solving inequalities. Again, here there's nothing really theoretical to talk about, so we're just going to run through some examples and talk about how to do this. So, x squared minus 4 is greater than 0. How many solutions am I looking for? No. It's an inequality. Infinitely many, right? So we have to be a little bit careful here. We're going to be writing our answer as a set, so using interval notation. To figure out the sets we need, I am going to go and first set it equal to 0. Now to solve this equal to 0, there are two solutions. And what I like to do is draw like a number line. On my number line, I'm going to put a dot at -2 and +2, because those are the only locations at my number line that the function can change sign, right? The only way that a continuous function can go from negative to positive is by passing through 0. When I draw my dot on my number line at -2 and +2, should I use an open circle or a filled circle? Open, why? Very good, because we have that standard strict inequality. Tells me that I'm going to be using open circles there. And then I'm just going to pick a test value in each of these intervals, and whatever the sign is in that interval is going to be the sign for the function everywhere in that interval. So if I plug -3 in for x, -3 squared is 9, -4 is 5. So that section is all positive. If I plug 0 in, 0 squared is 0, -4 is -4. So that section is all negative. And when I plug +3 in, it's going to be the same as what I got for -3, so that section is positive. So my solutions are going to be those two sections, because it's greater than. So we'll just say x is a member of -infinity to -2, and then +2 to +infinity. Do a couple more examples, make sure we got the hang of this. Sound good? So again, start by setting this equal to 0. How do I want to solve this? What's the first thing I need to do? Take out an x. Yeah. I notice the quadratic that remains factors, the two things that multiply to give me +4 and add to give me -4, are -2 and -2. So my solutions are 0, 2, and 2. All right. When I draw my number line and I put my dots on at 0 and 2, do I use filled dots or open dots? Filled this time. Why? Because it's an or equal to. Very good. So I'll pick some test values then. Again, does it matter what you pick for your test values? Not really. As long as it's inside the interval, you're good. So what do we get here? That's going to be a negative. And then I go put in 1. And that's going to be a positive. And I put in 3, 27 minus 36 plus 12 is also positive. So my solution is going to be just this section here, because it's a less than. Notice that I'm going to have to use what symbol at the 0? Bracket. Because we have a filled in circle as opposed to an open. Okay. I got 2 more examples and we're going to be donezo's. Sound good? All right. Next type of function here is a rational function. Notice it's not a polynomial, right? So is a rational function continuous everywhere? No. So we're going to have to worry about where can a rational function change signs then? At its 0 and its discontinuities. So the vertical asymptote is a type of discontinuity, so that answer was fine as well. It was more specific than I was looking for, but perfectly sufficient. Everybody's cool? Okay. All right. For the 4, open or closed? Should be open circle or closed circle for the 4. Closed. I've been using blue. Okay. -1, open or closed? It's open. Why? The function is undefined at the discontinuity. All discontinuities are going to be open circles regardless of whether the inequality is a strict inequality or an or equal to inequality. Everybody's good with that? School like that's just mean. Well, I'm a mean guy. It'd be more mean if I didn't tell you this stuff beforehand. So if I plug in -2, I have a negative over a negative, that's positive. If I plug in 0, I have a negative over positive, that's negative. If I plug in 5, I have positive over positive, that's positive. So my solutions then are those 2 parts. So notice that we're having to be careful here again because I get a parenthesis on the -1, but I get a bracket on the 4. Everybody's still okay? Again, not too difficult what we're doing. You just have to be a little bit careful because you have to be, there's lots of little details in here that can jump up and get you. I know, it's pretty scary. Math is terrifying sometimes, right?
I don't think it was the math.
It was that voice? All right. So like, oh, Boise, look at this guy. Well, we're going to do it the same way. So the numerator set equal to 0 is going to give me our zeros. So that's just going to be -4. Any questions with how I did that just in my head? Our discontinuity is going to come from the denominator set equal to 0. That's just going to be 1, right? Now, Mr. Kulak, I thought when we solved absolute values, you had to split it up or something. Well, yeah, you do, but the way you split it up is by taking the answer. One of them's positive, one of them's negative. But if the answer is 0, what's -0 is just 0, It's it's just 1. You know what I mean, guys? Okay. I just figured to remind you guys that absolute value equations typically have 2 solutions. Why does this one not have 2 solutions?
0.
Yeah, because it was equal to 0. That's right. Okay. Okay. If I plug in -5, what do you notice happens in the numerator? You're doing the square root of a negative. What's that mean? Undefined in this case, right? Inequality doesn't work for imaginary or complex numbers. That's not a defined operation. I plug in 0 and I get a positive. Oh, we forgot to do whether these, oh, I guess they're all opens, right? Since it's a strict inequality, there's not much to think about there. They all just have to be open circles. Forgot to do that. And I plug 2 in, I also get positive. So what do I want? I want this section and this section, right? So what? I can just do this. Everybody agree with that? You shouldn't be shaking your head yes at me right now. You should be like, Mr. Kulik, that ain't right. What's wrong with it? Yeah, there's a hole. There's a hole in my interval, dear Liza. So we got to write it that way. I know, right? The school gave you all the tricky things in the examples. You guys saw what the issue was? You can't write it as a single interval because there's a hole at 1. Okay. That closes up chapter 14 for us. That wasn't so bad. Next class we'll do chapter 12. We'll do that all in one day also. Bring your calculator if you don't usually bring your calculator. Chapter 12 is almost all going to be done on your calculator, which is cool, right? Right on, my dudes.
Oh, boy.
Oh, Boise. All right.